Welcome back to this second half of the today's lecture. We have seen how we think points as algebra homomorphisms and also how algebra homomorphisms gives us a K spectrum of a finite type K algebra. Now I want to spend little bit time about polynomial maps, because like we have defined group homomorphisms, ring homomorphisms, K algebra homomorphisms, we also need to define sometime morphisms between affine algebraic sets, and for that we need polynomial maps. So I want to collect some basic informations about polynomial maps, not polynomials but polynomial maps. Polynomial maps. So this is also interesting topic because it gives geometric language. See, whenever one thinks instead of a point, a map, the maps will lead to a geometry and the points will lead to sort of algebraic checking. So let us see. So as usual I will fix field K, K is a field, and A algebra over K. For this definition I will not even need it is a finite type algebra or such assumption. So arbitrary algebra. So what are the examples of arbitrary algebras, which one might ask how many. So we have seen very typical examples of polynomial algebra and residue class algebras of the polynomial algebra. These are the main objects for us to study in this course, but there are other interesting examples also which actually come from analysis. So just to give an example, let me give one example, because I don't want to give so many because we will run out of the time. So this is what you study in actually your first course on analysis. So what is it? So suppose I is a subset. Let us take very specifically, I is the closed interval AB in real numbers. And then what do we define? We define continuous functions on this closed interval, real valued. So that is C R, the suffix R is for real valued, the values go inside real numbers, and this is AB. So this is by definition F is a function from A to B, and real valued means image goes inside R, and we not study arbitrary functions, but F is continuous. On AB. Then we studied various properties of the continuous functions. For example, we study that if I have two continuous functions, then the sum is also continuous function. The sum is pointwise continuous. Sum is defined, sum of two functions is defined pointwise. So if f and g are two continuous functions, f and g are here, then f plus g is also there. F plus g is also continuous. Similarly, minus f minus g is also continuous. Similarly, minus f is also continuous. Similarly, the product function is defined by the value, multiply the product values, take the values and multiply their values. So that is the product function. This is continuous. Identity function is, identity means inclusion function here is continuous. What does this mean? This simply means that this CR AB is an R algebra. I just forgot to say that any constant function is continuous. So therefore it forms an algebra, and the first course analysis, now normally you study this algebra. So, that is R algebra. This is also called all these algebras which I will give, they are called function algebras. Just because their elements are functions. Okay, now continue. Now we want to take differentiable function. So, this is, I should need a notation, so I will write a 0 here. So, that is 0th differentiable function. Now, C R 1 a comma b. Now, what should it be? This should be 1 times differentiable continuous functions on the closed interval. I will not write because this is really only a digression for a language purpose and not much. And also we prove that every differentiable function is continuous. So, this is contained here. So, this is actually sub algebra of this, R sub algebra of this, and we can keep doing it. So, this contained in 2 times continuous differentiable functions on the closed interval, and so on, and n times. And then you ask whether is there a if this is proper, is there a continuous function which is not differentiable. Of course, you know that exists and so on. So, these inclusions are all proper. And also then you ask what is infinitely many. So, infinitely many times differentiable continuous function, that is denoted, that is also called C infinity function. So, this is the notation. You can go on further, and this is also all these stages proper, and the last one I will they are called analytic functions. Analytic functions means those functions which have power series expansion at a point, locally they have a power series expansion. So, this is also called omega here, AB, and also you can write down analytic function. There exists a C infinity function which is not an analytic function. So, these are proper inclusion, and these functions are also used actually in probability theory and so on. So, all these examples, now I fix a field R here. If instead of R you could take complex numbers, then this is called real analysis. If I replace R by C, then it will be called complex analysis. But complex analysis is better than real analysis, because in that case all these will become equalities. That is what is called Cauchy's integral theorem. So, every complex differentiable function is also complex analytic. So, all these algebras are called function algebras, and these algebras are not finite type algebras. They are different from finite type algebras, and therefore, whatever theory we will develop in this commutative algebra course, that will not be directly applicable here. So, with this that I explained, because there are examples of not finite type algebras over a field. All right. So, okay, we go on. Now, what do I mean by polynomial map? So, definition. For a polynomial, capital F in k x1 to xn, define a function on a power n by A is a given A algebra. So, I am defining f, I will call it, I want to denote it by the same letter f, from A power n to where? A power n to A. What is the definition? Take any tuple A which is A1 to AN. That means all these AIs are in the algebra A, and map it where? Map it to f of A. And remember, this is also in A, because see, let me just tell you in case of one variable what it happens. If I have a polynomial f in one variable, it looks like this: a0 x power m plus a1 x power m minus 1 m, this is not n, m minus 1 m minus 1 plus so on and so on plus am. This is not, I should not use a. So I should use different letters. So let me call it B's. Or alpha, alpha 0, alpha 1, alpha m, where alpha 0 to alpha m, they are elements in the field K. And when I plug it in now, what am I plugging it in? Capital X equal to small a. Small a is an element in the algebra A. So f of A is alpha naught a power m plus alpha 1 a power m minus 1 plus alpha m. But A is a K algebra, this was a K algebra. Therefore this makes sense. I can multiply A by A, I can multiply by a scalar, I can add these two. So this is indeed an element in A, and nothing special about one variable, the same thing for many variables. So therefore we do get a function on a power n, where n is the number of variables here. We get a function from there to there. Okay. So this function, to distinguish, I do not want to use a different notation really, but what I want to note is the following. When do I say that this a1 to an, this is where? This is in a power n. We say that this is a 0 of f if f of a is 0. That means this function vanishes at that a. And remember, this a is not in the field, a is not a tuple in the field, it is tuple in the given K algebra. So then you call it a 0 of f, alright. And this f, if you look at it as a function, so the function f from a power n to a is called the polynomial function defined by the polynomial f. In kx1 to xn. Now I just want to point out a danger in keeping the same notation. So for that, let me write an example. So example, let us take very minimal example. Z mod, so my field I choose to be Z mod 2. Then I know there are only two elements, 0 and 1, and I take polynomial in one variable only, fx, f in Z mod 2x, only one variable. And let us take f, first let us take f equal to x square plus x, x square minus x. And what is the polynomial function corresponding to this? What is my A? Let us take A also equal to this. A also equal to take that. You can take any algebra. But so now what is the function? The polynomial function f. This is from a power 1, n is 1. So, a power 1, that is a to a. What is the map? Where do any a go? Any a go to a square minus a. But a square minus a is a times a minus 1. And where is a varying? A is either 0 or 1. So, this f is actually identical 0 function. F is the 0 function. So, if I would have taken also instead of f 0 polynomial. So, let us take f prime equal to 0 polynomial. This is a polynomial. And then by this then we will get f prime is also 0 function. So, what I am trying to say that this polynomial f is not uniquely determined by this given function, and that will create a problem, and these phenomena will happen especially in case of a finite field. Definitely it will happen, because in a finite field there are finitely many functions actually, and there are infinitely many polynomials. So, many polynomials will give the same function. So, one remedy for that, in the beginning we should not denote by the same letter f, but then you should have some replacement also. So, what is the replacement one can do? This you can do it by phi and suffix f, and then I want to put a star here, which I cannot explain now, but I will explain when time comes. So, this function is defined by phi star suffix f evaluated at a is f evaluated at a, that is the definition. Okay, now let us prove some interesting things about these polynomial functions. For example, and this we will need it because we want to define functions on algebraic sets and not arbitrary functions, but what called polynomial functions. Alright, so what I want to prove is the following. If with the same notation earlier, if A, that A algebra, K algebra A we have started with, if A is an integral domain, infinite integral domain, not finite, infinite integral domain, then the polynomial functions phi star f determines the polynomial f uniquely. This is what I want to prove. So, infinite is very important, because we saw in finite integral domains are fields, and in field case, finite field case, we can always give functions which are polynomial functions, and the polynomial is not uniquely determined. Okay. And how do we prove this? This is proved by, so this will follow from the following identity theorem. So, I want to put this in a bracket. Okay. What is that? This will remind you that you might have studied the identity theorem in real analysis or complex analysis, and therefore, the following theorem is called identity theorem for the polynomial functions. So, theorem, this is the theorem. Let A be an integral. So, I will state in more general setup. So, let A be an integral domain and F, capital F, is a polynomial in several variables over A, Ax1 to xn, and this is a non-zero polynomial. If capital lambda 1 etc., capital lambda n, they are subsets of A with cardinality of A, not A, lambda I, capital lambda I is bigger than, strictly bigger than degree in xi of f for all i's from 1 to n. Then I will digress you by giving a, before I prove this, I will digress you by giving a concrete examples in a special situation. Then if I call this capital lambda to be the product of these sets, which is each one of them is in A, therefore this is in A power n, which is this set, product set is not contained in, now I will use the notation V A F. What is this should mean? This means zeros of f in A. So, let us write it, this is all those tuples A, which is A1 to An in A power n, such that capital F substituted A is 0. This one was a subset in, this one by definition is a subset in A power n. See, this is a subset in A power n, this is also a subset in A power n. If this condition is given for all i's, then this set is not contained here. That means what we have to produce? We have to produce a tuple in A power n, which f does not vanish on that. That is the assertion. In particular, so this is what we prove, this is a more general statement, and what is the consequence I am writing in particular. So, maybe I write in a different color. In particular, there exist A1 A equal to A1 to An in this capital lambda such that f of A is non-zero, that is, it is not here, an element here which is not here. In particular, if A is infinite, moreover, if A is infinite, do not worry about the proof will be very easy. So, infinite, so far this is for general integral domain I wrote a statement. Now, in particular, if A is infinite, then the evaluation map, evaluation or substitution also we are calling it, no, substitution map from where to where, that is denoted by epsilon. This is from the polynomial algebra over A infinitely many variables, n, this many, n is given here, 2 where 2 maps from A power n to A. What is the map? What is this map? This is given by f, a polynomial f with coefficients in A, that is mapped to what do I call it, epsilon. So, epsilon f, and epsilon f is by definition, this should be a map. This should be a map from A power n to A. And what is that map? Take any A here and evaluate at f, that is f of A. It's clear? So, polynomial goes to a map from A power n to A, this is f of A. What about this? The evaluation map is injective. That is what we wanted to prove, that two polynomials cannot go to the same polynomial function. This map is injective means that polynomial f is, the polynomial f here is uniquely determined by its function. So, this is what we want to prove. This is very easy, let us see it. Okay, so proof. I am going to prove this assertion by induction on n, induction on the number of variables. So, proof by induction on n, which is the number of variables. All right. For n equal to 0, it is trivial. N equal to 0, it is trivial. Now I have to prove, my induction started at n equal to 0. Now I will prove the inductive step. For the inductive step, that means what? That means I will assume the step from n minus 1 variable case to n, we need to prove. So, what is our assumption now? Inductive hypothesis is given a polynomial over A in n minus 1 variables with the same assumption, that is the degree is smaller than the sets, and then we want to prove for n. Okay, so, let us see. So, now what we have given a polynomial f. So, write polynomial f as a polynomial in the last variable. So, this you can write it as a summation. Summation will be from k to d. This is a polynomial, think of this a polynomial in first n minus 1, coefficients are in first n minus 1 variable. So, there will be some the coefficients f k's, they will be polynomials in first n minus 1 variables x n power k. So, you are thinking this is a polynomial in A x1 to xn minus 1, and this is our new base ring, and then to that this is xn. So, we have written in this way with the degree d, with d equal to degree in xn of f, that is the last coefficient f suffix d x1 to xn minus 1, this is non-zero. And this is a non-zero polynomial in this polynomial ring. And obviously, what is the assumption that we need to conclude? It is this one. So, look at the degree in the variable xi of the polynomial fd. So, I is from 1 to n minus 1, this is 1 here. So, the degree in ith variable cannot be more than the degree in ith variable in f, because that term times this will definitely be degree. So, this is smaller equal to degree in xi of the polynomial given polynomial f, but this is strictly less than the cardinality of that capital lambda I. This is the assumption. So, I have a polynomial in n minus 1 variable, and I have this, and this is true for I equal to 1 to n minus 1. I have these subsets whose cardinality is strictly bigger than this degree. So, what can I conclude by induction? I can conclude by induction that there exists an n minus 1 tuple where I evaluate this FD at that n minus 1 tuple, this is non-zero. Therefore, by induction hypothesis, because we are assuming the statement for n minus 1 variables, there exists a point a1 to an minus 1 in a power n minus 1 with, when I evaluate fd at a1 to an minus 1, this is non-zero. This is the induction hypothesis. So, plug it in there. So, when I plug this here, that means I am substituting x1 equal to a1, x2 equal to a2, xn minus 1 equal to n minus 1 on this side. So, therefore, we get f of a1 to an minus 1 comma xn variable I do not change this equal to summation k equal to 0 to d capital Fk evaluated at a1 to an minus 1 times x power n power k. We get this. This is a polynomial in with coefficients in A. So, this is a polynomial, these coefficients are in A. This is a polynomial over A in xn variable. And what is the degree of this polynomial? You see, the last coefficient of x power d is precisely this. This is precisely this. Therefore, and degree of f of a1 to an minus 1 comma xn is still equal to d, since coefficient of degree coefficient of xn power d is f of a1 to an minus 1 fd of this, which is non-zero, that we have noted. So, the degree of this polynomial is d. Now, it is a d degree polynomial. This is a polynomial in axn. A is an integral domain, and remember, A is an integral domain. So, this polynomial cannot have more than d zeros, but cardinality of that capital alpha d, capital gamma d, this cardinality is more than degree of xd degree of f, which is precisely not xd, xn. this which is d, which is this degree d. So, I have a polynomial in one variable with coefficients in an integral domain whose degree is d, and this subset has cardinality more than d. So, there will be at least one element where it is not 0. So, there exists point, there exists a n, this is not d, sorry, this is n. There exists a in a n, lambda, capital lambda n, let us call it a n, such that this polynomial, this one evaluated x n equal to this a n, it will not be 0. Capital F of a 1 to a n minus 1 comma a n, this is non-zero, since A is an integral domain. So, we proved it. We found a point a 1 to a n in a power n, so that this polynomial evaluated that is non-zero. So, we proved, so this proves the theorem, and remind you what I wrote later is a easy consequence of the earlier statement. See, one more step I have to go back. Here we wanted to prove there exists some element here which is not in VAF, that means f is not 0 there. In particular, this follows immediately. If it is infinite, then it follows immediately, because each polynomial will have at least one tuple which is non-zero there. So, that proves the thing, and with this I will continue in the next lecture, and I will basically I want to study more polynomial functions, and then I will also come back to the properties of the, I will come back to affine algebraic sets and properties, and using them I will define what is a topology. That topology will be called Zariski topology, and then we will relate this Zariski topology to the maximal spectrum and spectrum, and that topology, with that topology, these two topological spaces, actually three topological spaces, one is a K spectrum, the other is a maximal spectrum, and the other is a prime spectrum. We will study the topologies on this set defined by these algebraic sets, and that is precisely algebraic geometry. For K spectrum it is classical, and for maximal spectrum it will still be little bit more generalization of classical algebraic geometry, and for the spectrum it will become a full modern algebraic geometry, and in this course I will only stick to affine algebraic geometry. Thank you.